Deep in the constellation Leo, 120 light-years from Earth, a telescope has captured something that will forever alter our place in the cosmos. It is a discovery so profound, it redefines the very definition of being alive and confirms humanity's most ancient, desperate hope. We are not alone. Floating a million miles from our world, the James Webb Space Telescope has detected a planet where the chemical signature of living creatures pulses in an alien atmosphere. Scientists are not merely hopeful or intrigued. They are 99.7% certain they have found it. A world teeming with biological activity. A planet that might be even more suited for life than Earth itself. This is not a story about what we might find one day. This is the story of what we have already found. Before we journey to this distant world and witness the dawn of a new era in human history, make sure you are subscribed and have enabled notifications. This is a voyage into the unknown, and you won't want to miss a single discovery that lies ahead. Now, prepare yourselves. We are about to uncover the first undeniable signs of life beyond Earth. The data arrived on a Tuesday morning, buried in terabytes of infrared light captured by humanity's most powerful eye in space. At Cambridge University, Dr. Nikku Madhusudan stared at his computer screen, watching wavelengths of light that had traveled for more than a century to reach his instruments. What he saw made his hands tremble. There, in the spectrum of light filtered through the atmosphere of a world designated K2-18b, was a signature that should not exist. Dimethyl sulfide, a molecule that, on our planet, is produced exclusively by living organisms. This wasn't a faint trace or a statistical ghost. The signal was so strong, so clear, that the odds of it being a mistake were less than 3 in 1,000. The James Webb Space Telescope, a marvel of engineering so sensitive it could detect the heat signature of a bumblebee on the moon, had found the undeniable fingerprint of life. In the world of astronomy, where certainty is a rare luxury and discoveries are often overturned, a 99.7% confidence level, a 3 sigma detection, is the gold standard. It's the same statistical threshold used to confirm the existence of the Higgs boson and detect the faint ripples of gravitational waves. We are as certain that something is alive on K2-18b as we are about some of the most fundamental discoveries in modern physics. The world itself, K2-18b, orbits a red dwarf star in the habitable zone, that perfect region where liquid water can exist. But this is no Earth twin. It is a colossal planet, 8.6 times more massive than our own, belonging to a class of worlds called super-Earths. It's wrapped in a thick, hydrogen-rich atmosphere, an environment once thought to be completely inhospitable. Yet this very atmosphere creates a greenhouse effect so perfect that it maintains a surface temperature of a steady 120 degrees Fahrenheit, the temperature of a warm summer day, ideal for vast liquid water oceans to thrive beneath alien skies. For months, Madhusudan's team had been studying this world, using the JWST's incredible power to dissect the starlight filtering through its atmosphere. Each time the planet passed in front of its star, a transit, it revealed new secrets. First, they found water vapor. Then came methane and carbon dioxide, a cocktail of gases that on Earth points to a dynamic planetary metabolism. But dimethyl sulfide was the game changer. It is what scientists call a biosignature, a molecule so intimately and uniquely connected to biological processes that finding it is like discovering a flashing neon sign advertising life. The implications were staggering. If confirmed, this single discovery would end humanity's cosmic loneliness forever. We would no longer be a solitary accident in a silent universe, but part of a vast, living cosmos. The numbers told a story so profound it felt almost mythological. 99.7% confidence. Life, breathing, 120 light-years away. But the discovery was just the beginning. The world itself was the true revelation. Scientists had long believed that the search for life meant searching for a mirror of our own world, a rocky planet with a nitrogen atmosphere orbiting a sun-like star. K2-18b shattered that assumption completely. The evidence was undeniable, but the world it pointed to should have been impossible. It was a new type of planet, a Hycean world, and it would force us to rewrite the rules for finding life in the universe. A video from the University of Cambridge provides further insight from Professor Nikku Madhusudhan on the detection of potential biosignatures in the atmosphere of K2-18b. For decades, the search for extraterrestrial life was a search for ourself. Our telescopes scanned the darkness for an Earth 2.0, a rocky planet orbiting a sun-like star at just the right distance for liquid water to pool on its surface. We were looking for a mirror, a cosmic twin that would validate our own existence. But K2-18b shattered that mirror completely. It proved that life could emerge and even thrive in conditions so profoundly alien that we had previously dismissed them as impossible. This world belongs to a class called super-Earths, planets larger than our own but smaller than gas giants like Neptune. And until this discovery, astronomers had largely written them off as inhospitable gas balls, too massive and with atmospheres too crushing to support life as we know it. K2-18b forced scientists to reimagine what a habitable world could truly be. Its sheer size is the first barrier to our Earth-centric intuition. At 8.6 times the mass of our world, K2-18b's surface gravity is nearly 3 times stronger. A person weighing 150 pounds on Earth would feel as if they weighed over 400 pounds on its surface, an immense pressure that would make every step a monumental effort. Yet, this crushing weight, once seen as a deal-breaker for habitability, might actually be the secret to its success. This intense gravity holds the planet's atmosphere in place with an iron grip, preventing it from bleeding away into space. Billions of years ago, Mars lost its atmosphere to the solar wind, turning from a wet, warm world into a frozen desert. K2-18b, protected by its own mass, would never suffer such a fate. Its atmosphere is eternal. And what an atmosphere it is! It defies everything we know about habitable worlds. Instead of the familiar nitrogen and oxygen we breathe, the air on K2-18b is a thick envelope dominated by hydrogen and helium. On Earth, hydrogen is a forgotten trace gas, making up less than 1 part per million of our air. On K2-18b, it is the primary component, creating an environment fundamentally different from our own. This hydrogen-rich atmosphere acts like a planetary blanket, creating an insulating effect far more powerful than Earth's. It traps the heat from its star with perfect efficiency, redistributing warmth so effectively that the entire planet maintains a stable, life-friendly temperature. Even the night side of the planet, tidally locked in perpetual darkness, remains warm enough for vast liquid oceans to exist.
Think of the implications. Life on Earth is constantly stressed by temperature swings. Animals migrate, hibernate, or develop complex physiologies simply to survive the transition from day to night, from summer to winter. On K2-18b, life faces no such challenge. In a world of eternal, stable warmth, organisms could invest all of their energy into growth, reproduction, and evolution, rather than mere survival. The chemical signatures detected by the JWST paint a picture of a world where life has not only emerged, but has become a dominant geological force. Alongside the stunning detection of dimethyl sulfide, the atmosphere is rich with methane, carbon dioxide, and water vapor, a cocktail of molecules that, on Earth, points to a planetary-scale metabolism. But perhaps the most shocking evidence comes from what is missing. The telescope found no trace of ammonia. In a hydrogen-rich atmosphere without life, ammonia should be abundant. Its absence is a profound clue. It suggests that biological processes are actively scrubbing it from the air, consuming it as part of a planet-wide biochemical cycle. Life is not just a passive passenger on this world. It is in the driver's seat, actively shaping the chemistry of its own atmosphere. The discovery of K2-18b has opened a new frontier. It tells us that red dwarf stars, which make up 3/4 of all stars in our galaxy, are prime targets in the search for life. The number of potentially habitable worlds in the cosmos could be hundreds, even thousands times larger than we ever imagined. We are not looking for Earth's twin anymore. We are looking for its strange, more robust cousin, thriving in conditions we are only now beginning to comprehend. To trust this impossible discovery, however, we needed an instrument capable of seeing the unseeable. A technological marvel floating 1,000,000 miles from home, with a golden eye so powerful it could read the chemical story of a world's breath across 120 light-years of silence.
The James Webb Space Telescope is not just an observatory. It's a monument to human ambition, a time machine floating in the void. Positioned 1,000,000 miles from Earth at a point of perfect gravitational balance called L2, the telescope exists in a state of perpetual darkness. Its massive 5-layer sun shield, the size of a tennis court, blocks all heat and light from our star, keeping its instruments colder than the surface of Pluto. In this frigid isolation, Webb can see the universe in a way no instrument before it ever could. Its primary mirror is a breathtaking work of art and engineering, a 21-foot-wide mosaic of 18 hexagonal segments, each coated in a microscopic layer of pure gold. This golden honeycomb is not for aesthetics. Gold is the perfect reflector of infrared light. When these segments work in perfect unison, they form a single, flawless mirror so powerful it could detect the heat signature of a bumblebee on the surface of the moon. This extraordinary sensitivity to infrared light is the key to finding life on distant worlds. Infrared is the light of heat, the glow of molecules, the invisible language of atmospheric chemistry. When a planet like K2-18b passes in front of its star, a tiny fraction of the starlight filters through its atmosphere. As it does, molecules in the air absorb specific wavelengths of infrared light, leaving behind a unique chemical fingerprint, a transmission spectrum. Water, methane, and dimethyl sulfide each leave their own distinct mark, a pattern of dark lines in the spectrum that tells a story across 120 light-years. Reading this story is a challenge of almost incomprehensible difficulty. The star, K2-18, is billions of times brighter than the planet orbiting it. Detecting the faint absorption lines from the planet's atmosphere is like trying to spot the shadow of a gnat flying in front of a distant searchlight while standing 1,000 miles away.
To achieve this impossible feat, Webb's engineers equipped it with a secret weapon, a suite of advanced coronagraphs. Originally designed to study our own sun by blocking its blinding light, these devices have been adapted to hunt for exoplanets. A coronagraph works like a precisely engineered eclipse. An intricate system of masks and mirrors is positioned to block the overwhelming glare of the star, allowing the much fainter light from the planet's atmosphere to pass through. The process is like using a sophisticated audio filter to remove the deafening roar of a jet engine so that you can hear a single, delicate whisper underneath. Even with the starlight suppressed, another challenge remains. Tiny imperfections in the telescope's own optics create false signals called speckles that can mimic the light from a planet. Here, artificial intelligence comes into play. Advanced computer algorithms analyze millions of data points in real time, learning to distinguish between genuine planetary signals and optical noise with superhuman precision. The detection of dimethyl sulfide on K2-18b pushed this technology to its absolute limits. The molecule produces an infrared signature so faint that it took Webb multiple observations spread over several months to confirm its presence beyond any statistical doubt. Each observation captured just a handful of photons that had completed their 120-year journey from an alien world, carrying with them the secret of extraterrestrial life. The telescope's instruments measured the wavelengths of this ancient light to an accuracy of 1 part in 10 million, a feat of precision equivalent to measuring the width of a human hair down to the size of a single atom. Webb has fundamentally changed our relationship with the cosmos. We are no longer just looking up and wondering. We are actively reaching out with our instruments, reading the atmospheric stories of distant worlds. The data processing, the artificial intelligence, the sheer engineering genius, it all pointed to one unbelievable fact: life. But this life wasn't just surviving in a harsh environment, it appeared to be thriving in a planetary paradise. The telescope revealed a world maintained at a perfect, stable temperature, a cosmic haven heated to exactly 120 degrees Fahrenheit.
The implications for life are staggering. In this planetary hot tub, organisms would not need to waste energy surviving environmental extremes. They would be freed from the evolutionary pressure of adapting to freezing winters or searing summers. This stability could allow life to invest its resources into developing greater complexity, diversity, and perhaps even intelligence at a rate far faster than on Earth. And at 120 degrees Fahrenheit, the conditions are not just survivable, they are biochemically ideal. Laboratory experiments showed that this temperature is a sweet spot where the chemical reactions essential for life proceed rapidly, but not so fast that they break down the delicate organic molecules that form cells. It mirrors the temperatures found in some of Earth's most vibrant ecosystems, like the deep-sea hydrothermal vents where life thrives on chemical energy in the absence of sunlight. In a cosmos where most known worlds are either frozen wastelands or molten hellscapes, K2-18b stands as a beacon, a testament to the universe's ability to create conditions not just permissive of life, but actively conducive to it. In this perfectly regulated paradise, life would have every advantage. But to be certain it was actually there, to move from probability to proof, scientists needed more than just the right temperature. They needed a chemical whisper from across the void, a single molecule so specific it could only have one source, a biological one.
120 degrees Fahrenheit. The number seems almost too perfect, a temperature engineered for comfort and life. It is the warmth of a hot summer day in a desert oasis, the heat of a therapeutic hot spring, the feverish intensity of a body fighting for life. On K2-18b, it is the temperature that makes life possible across the entire surface of a world. Temperature is the master variable in the equation of life. Too cold and water freezes solid, locking away the potential for the complex chemical reactions that biology requires. Too hot, and that same water boils away into steam, sterilizing the surface and leaving behind a lifeless, scorched desert. The narrow band where liquid water can exist, what scientists call the habitable zone, is a sliver of cosmic real estate so precious that finding a planet within it is cause for celebration. Earth sits comfortably in the middle of this zone, a fortunate accident of orbital mechanics that has allowed life to flourish for 4 billion years. But the perfect temperature on K2-18b is no accident. It is the result of a delicate, self-regulating balance between the energy from its star and the chemistry of its atmosphere, a system that may create conditions far more stable than anything found on Earth. The planet orbits its cool red dwarf star at a distance that provides it with almost exactly the same amount of energy per square meter as Earth receives from our Sun. This cosmic coincidence places it squarely in the Goldilocks zone, not too hot, not too cold, but just right. However, it is the planet's hydrogen atmosphere that elevates it from merely habitable to a potential paradise. This thick, insulating envelope acts as a planetary thermostat, trapping and redistributing heat with breathtaking efficiency. On Earth, we are accustomed to dramatic temperature swings. The scorching heat of day gives way to the chill of night. The warmth of the equator contrasts with the frozen poles. Seasons dictate the rhythm of life, forcing organisms into cycles of growth, hibernation, and migration. Our planet's thin nitrogen atmosphere is a leaky container, allowing heat to escape rapidly back into space. K2-18b's hydrogen blanket changes that dynamic completely. The planet is tidally locked, meaning one side perpetually faces its star in eternal daylight, while the other is cloaked in endless night. On a world like Earth, this would create an uninhabitable furnace on one side and a frozen wasteland on the other. But on K2-18b, powerful atmospheric currents carry warmth from the day side to the night side, creating a planet where the entire surface maintains a consistent, life-friendly temperature.
Dimethyl sulfide. The name is clinical, unremarkable. But on Earth, this simple molecule carries the unmistakable scent of life. It is the smell of the sea, the aroma of vast phytoplankton blooms breathing in the sunlit oceans, the chemical exhale of a living planet. When the James Webb Space Telescope detected this molecule in the atmosphere of K2-18b, it found more than just a complex gas. It found the chemical echo of an alien ocean, a scent carried on photons across 120 light-years of silent, empty space. This discovery represents the most important breakthrough in human history, because on our world, dimethyl sulfide is produced exclusively by living things. No known geological process, no volcanic eruption, no non-living chemical reaction has ever been observed creating it. It is, in the truest sense of the word, a biosignature. For decades, scientists debated what definitive proof of alien life would look like. Many assumed it would be the detection of oxygen, the gas that sustains complex life on Earth. But oxygen can be a cosmic false positive. It can be produced by non-biological processes like water vapor being broken apart by intense starlight. Methane, too, can be ambiguous, released by both bacteria and geological activity. Finding oxygen or methane would be exciting, but it would leave room for doubt. It would be like finding a footprint in the sand. It suggests someone was there, but the print could have been made by the wind or the water. Dimethyl sulfide, however, is not a footprint. It is a detailed, undeniable fingerprint. Its presence can only be explained by biology. The molecule's chemical structure tells a story of sophisticated evolution. Composed of a sulfur atom bonded to carbon-containing methyl groups,
Dimethyl sulfide requires specific, complex enzymes to be constructed. These are not simple reactions that happen spontaneously. They are the products of an intricate biochemical factory that has been fine-tuned over millions or perhaps billions of years. The fact that life on K218b has evolved the machinery to produce this exact molecule suggests something profound about the universe. The basic chemistry of life might be universal. The same evolutionary pathways, the same molecular solutions may arise again and again on worlds scattered across the galaxy. Life may not just be common, it may follow a predictable script.
But the most staggering part of this discovery is the sheer abundance of dimethyl sulfide in K218b's atmosphere. The signal detected by Webb was not a faint marginal whisper. It was a clear, strong signature, indicating that the molecule is a significant component of the planet's air. For this chemical to be detectable from 120 light-years away, the biosphere on K218b must be producing it on an unimaginable scale. We are not talking about a few isolated colonies of microbes clinging to life in a hostile world. We are talking about a planetary ecosystem so vast, so productive, that it is fundamentally altering the chemistry of an entire world's atmosphere, broadcasting its existence across interstellar space. This is the signature of a planet that is deeply, profoundly alive. The dimethyl sulfide is likely produced by organisms in K218b's vast hydrogen-water oceans, analogous to the phytoplankton in our own seas. The scale of production suggests these oceans are teeming with life, a global biosphere that has been active for a very long time. For the first time, we had found the signature of life itself. But in science, a signature is not enough. We needed certainty. We needed proof so statistically powerful that it would be undeniable, leaving no room for doubt or alternative explanations. And when the final numbers came in, they delivered a verdict that would echo through history. A 99.7% chance that we had finally found our cosmic neighbors.
In the world of science, certainty is a currency earned through relentless skepticism and brutal statistical analysis. Scientists are trained to doubt, to question, to search for every possible flaw in their own discoveries. But when the data from K218b was subjected to this crucible, the numbers told a story so clear, so statistically powerful, that even the most hardened skeptics were forced to listen. A 99.7% chance. This isn't a guess or a hopeful estimate. It is a mathematical statement of confidence, a scientific verdict delivered with the weight of undisputed physics. To understand what this number truly means, we have to understand how scientists measure certainty itself. They use a statistical scale called sigma. A 1 sigma detection is little more than a hint, a statistical bump that has a good chance of being random noise. A 2 sigma detection is intriguing, but still not enough to claim a discovery. The gold standard, the threshold at which a signal is accepted by the scientific community as a genuine discovery, is 3 sigma. A 3 sigma detection means there's a 99.7% chance the signal is real, and only a minuscule 3 in 1,000 probability that it is a random fluke. This is the same statistical barrier that was crossed to announce the discovery of the Higgs boson at the Large Hadron Collider, and to confirm the first detection of gravitational waves. The biosignature on K218b has met that same standard of proof. Reaching this level of confidence for something as faint as an alien atmosphere 120 light-years away required a process of almost fanatical rigor. The team didn't just see the dimethyl sulfide signal once. Webb's instruments observed the planet multiple times over several months as it passed in front of its star. Each and every time, the same molecular fingerprint appeared in the data. Different instruments on the telescope, each with its own detectors and potential for error, independently confirmed the signature, providing redundant verification. The team's computer algorithms then went to war with the data, trying to kill the discovery.
They searched for any systematic error, any instrumental glitch, any contamination from Earth's own atmosphere that could be mimicking the signal. None were found.
They modeled every known non-biological chemical reaction that could possibly occur in a hydrogen-rich atmosphere, trying to find an alternative explanation. Every abiotic model failed to reproduce the observed data. The only explanation that fit, the only one that survived every attempt to disprove it, was biological activity on a planetary scale. The statistical improbability of this being a false alarm is difficult to overstate. Imagine flipping a coin 1,000 times. The odds of it landing on heads 997 times are so infinitesimally small that it would essentially never happen by chance in the entire history of the universe. That is the level of confidence we have that the dimethyl sulfide on K218b is real. This isn't just a possibility anymore. In the cautious, evidence-based language of science, this is as close to a proven fact as we can get without sending a probe. We are no longer asking if life exists elsewhere. We are now asking what that life is like. The numbers were irrefutable, the statistics ironclad. Life was there. But the world it inhabited was nothing like Earth. The source of this powerful biosignature, the cradle of this alien biology, wasn't a familiar ocean of water under a nitrogen sky. It was something far more exotic. A vast, planet-spanning ocean of water mixed with hydrogen, a chemical environment that would rewrite the very definition of a habitable world.
Beneath the swirling hydrogen clouds of K218b lies an ocean unlike anything in our solar system. Forget the familiar saltwater seas of Earth. This is a realm of profound alienness, a global ocean not of water alone, but of water infused with hydrogen under pressure so immense they would instantly crush any submersible we have ever built. Yet, in one of the great paradoxes of astrobiology, this seemingly hostile environment might be the most life-friendly place we have ever discovered. This hydrogen ocean exists because of the unique interplay between the planet's massive gravity and its thick atmosphere. The immense pressure forces atmospheric hydrogen to dissolve directly into the liquid water, creating a chemical solution with truly remarkable properties. Pure water, as we know it, can only remain liquid within a narrow temperature range. But this hydrogen-water mixture can exist as a stable liquid from near freezing all the way up to 300 degrees Fahrenheit, vastly expanding the range of conditions in which life could thrive. On Earth, the deepest part of our ocean, the Mariana Trench, is a realm of crushing darkness. The pressure there is over 1,000 times greater than at the surface, a force that would collapse the cellular structures of most life forms. But on K218b, the hydrogen dissolved in the water is thought to act as a natural pressure buffer. It changes the physical properties of the water itself, allowing it to remain a gentle medium for life, even at depths that would be fatal on Earth. The very element that makes the pressure extreme also makes it survivable. This bizarre ocean also solves one of the greatest long-term threats to habitability: atmospheric loss. Over billions of years, Earth is slowly losing its atmosphere to space as light gases escape our planet's gravitational pull. In the distant future, our world will become as airless and barren as Mars. K218b, however, has a permanent solution. Its vast ocean acts as a massive atmospheric reservoir. As hydrogen is inevitably lost to the vacuum of space, more of it simply dissolves out of the ocean to replenish the air, creating a stable atmosphere that could potentially persist not for billions, but for trillions of years. This chemical environment opens up possibilities for life that would be impossible on Earth. Hydrogen is a potent energy source. On our world, only a few specialized bacteria have learned to metabolize it, limited by its scarcity. But on K218b, organisms could literally breathe the ocean itself. In an environment where the primary fuel for life is dissolved into the very water they live in, ecosystems could flourish with an energy budget that is virtually unlimited.
These hydrogen-metabolizing organisms would be fundamentally different from anything on Earth, producing entirely different chemical signatures. The dimethyl sulfide detected by Webb might be just one of many biosignatures in an alien ecosystem built on a foundation of hydrogen chemistry. The depth of this ocean remains a tantalizing mystery, but computer models suggest it could be hundreds of miles deep, dwarfing all of Earth's oceans combined. This colossal volume of liquid, stable for eons and rich with energy, could harbor ecosystems of unimaginable complexity and diversity. We are no longer just looking for worlds like our own. The discovery of K2-18b's hydrogen ocean suggests we should be looking for worlds that might be better than Earth. In the deep, warm, hydrogen-rich seas of super-Earths, life may not just be surviving, it may be thriving in ways that make our own biosphere seem fragile and limited by comparison. This vast, stable, energy-rich ocean could harbor life on a scale we can barely comprehend. But the wonders of K2-18b are not confined to its depths. Above this alien sea swirls an atmosphere of pure spectacle, a chemical cocktail where methane clouds drift through hydrogen skies, and where, under the right conditions, the pressure becomes so great that carbon itself crystallizes and falls, as a constant, glittering rain of diamonds.
The atmospheric chemistry of K2-18b is a spectacle of alien science, a complex cocktail of molecules that creates conditions both bizarre and breathtakingly beautiful. While Earth's sky is a simple, predictable mix of nitrogen and oxygen, the air on K2-18b is a dynamic, living system. Methane, a gas that on Earth is a fleeting byproduct of life, swirls through clouds of hydrogen. Carbon dioxide, a trace gas in our world, forms crystalline structures in the upper atmosphere. And under the planet's immense pressure, carbon atoms are squeezed into a form we consider the most precious on Earth: diamonds. The presence of so much methane in K2-18b's atmosphere is, by itself, a profound mystery that points to life. This simple molecule is highly reactive and should break down quickly when exposed to the ultraviolet radiation from its star. On Earth, methane only persists because it is constantly replenished by biological sources, from bacteria decomposing matter in swamps to the metabolic processes of countless animals. The fact that Webb detected vast quantities of it on K2-18b means something there is actively producing it, pumping it into the air on a planetary scale. But the methane on this world may be far more than just a waste product. In the unique chemistry of a hydrogen-rich atmosphere, it could serve as a crucial energy source. Just as life on Earth is built around an oxygen cycle, with plants producing it and animals breathing it, life on K2-18b could be built around a methane cycle. Some organisms might produce it, while others consume it for fuel, creating a completely alien metabolism where life literally breathes a flammable gas. This atmospheric dance creates conditions that seem like pure fantasy. At certain altitudes, the combination of pressure and temperature is perfect for compressing carbon atoms into diamond crystals. These microscopic diamonds would form high in the atmosphere and then rain down towards the surface, creating a constant glittering shower. To any life forms on K2-18b, this diamond rain might be as common and unremarkable as water rain is to us, a normal part of a weather cycle that brings a different kind of treasure from the sky.
The substantial amounts of carbon dioxide add another layer of complexity. This gas interacts with the abundant hydrogen and methane in ways that could support forms of photosynthesis completely unknown on Earth. Instead of using sunlight to turn water and CO2 into sugar and oxygen, organisms on K2-18b might have evolved to use the red-shifted light of their star to create energy from hydrogen and methane, producing byproducts we have yet to even imagine.
This entire chemical factory is regulated by a planet-wide weather system of incredible scale. Because the planet is tidally locked, massive atmospheric currents, like global conveyor belts, constantly circulate air from the hot, sun-drenched day side to the cool, dark night side. This perpetual mixing creates a remarkably stable global climate, ensuring that the atmospheric chemistry remains in equilibrium across the entire surface. Perhaps most importantly, this thick, churning atmosphere serves as the ultimate shield. Red dwarf stars like K2-18 are known for their violent tempers, frequently erupting in powerful flares that can blast nearby planets with lethal radiation. A planet like Earth, with its thin atmosphere, would be sterilized. But K2-18b's dense hydrogen envelope absorbs and deflects these stellar tantrums, creating a safe harbor on the surface where life is protected from its own star's fury. This living, breathing atmosphere, a shield against radiation, and a cradle for exotic chemistry, is only possible because of the star K2-18b orbits. It is not a star like our Sun, a brilliant, hot giant destined to burn out in a few billion years. Instead, it is a red dwarf, a small, cool, and impossibly ancient star that offers its planet the one thing more valuable than warmth: time. Trillions of years of it. K2-18 is not a star like our Sun. It is a red dwarf, smaller, cooler, and far dimmer than the brilliant yellow star that anchors our solar system. For decades, these faint reddish stars were considered cosmic backwaters, too volatile and too weak to support life. But K2-18b has forced us to see them in a new light. These unassuming stars, the most common type in the universe, may in fact be the greatest cradles of life in the cosmos, offering a gift more precious than sheer energy, an almost eternal stretch of time. Our Sun is a magnificent but fleeting spectacle. It has a lifespan of about 10 billion years, and it is already halfway through its life. In another 5 billion years, it will swell into a red giant, a monstrous, expanding ball of fire that will boil away Earth's oceans and consume the inner planets, extinguishing any life that remains. Our world has an expiration date. Red dwarfs like K2-18, however, are paragons of stellar efficiency. They make up roughly 75% of all stars in our galaxy, and they burn their nuclear fuel so slowly and methodically that they can shine for trillions of years. While our Sun is a roaring bonfire destined to burn out, a red dwarf is a slow-burning ember that will provide steady, reliable warmth for a duration that makes the current age of the universe seem like a brief flash. This incredible longevity has profound implications for the development of life. On Earth, complex life took nearly 4 billion years to evolve from simple single-celled organisms to the rich biosphere we see today. If life on K2-18b has had even a fraction of the time available to it, it could have reached levels of complexity and sophistication that would make our own world seem primitive by comparison. With trillions of years to evolve, life on a red dwarf planet could achieve things we can't even begin to imagine. Of course, life around a red dwarf faces unique challenges. Because the star is so cool, the habitable zone is much closer. K2-18b completes a full orbit in just 33 days, zipping around its star at a distance that would place it well inside the orbit of Mercury in our own solar system. This proximity leads to a phenomenon called tidal locking, where the planet's rotation is synchronized with its orbit. The result is a world with one side locked in perpetual daylight and the other in eternal night. This could create a planet of two extremes, a scorching, furnace-like day side and a frozen, barren night side. Life, if it exists, would likely be confined to the Terminator Zone, a band of perpetual twilight that rings the planet, where temperatures are just right. Another major threat is the volatility of red dwarfs. Many are known to be tempestuous, erupting in powerful stellar flares that can blast their planets with lethal doses of X-rays and charged particles, stripping away atmospheres and sterilizing surfaces. But here again, K2-18b appears to be exceptionally fortunate. Its host star is what astronomers call a well-behaved red dwarf, a mature and stable star with minimal flare activity, providing a calm and predictable environment for life to flourish. Even the quality of light is different. The star's reddish hue means that plant life would need to adapt to a spectrum heavy in infrared light. Photosynthesis would require different pigments, and alien forests might appear black to our eyes. Their leaves evolved to absorb every possible photon of the faint red light. This is a world with every advantage: a stable star, a protective atmosphere, a perfect temperature, and an ocean rich with life. A world with trillions of years ahead of it. It is, in every sense, a cosmic paradise, but it is a paradise separated from us by an ocean of darkness so vast it defies comprehension. A gulf of 120 light-years.
K2-18b is unlikely to be a singular miracle. The statistical probability suggests it is merely the first one we have found, the closest example of a phenomenon that likely repeats itself billions of times over across the Milky Way. Our local neighborhood of stars, a sphere just a few hundred light-years across, could be teeming with living worlds, each having followed its own unique evolutionary path. The galaxy may not be a vast, sterile desert with a few rare oases. It may be a lush, vibrant jungle, filled with life in every conceivable form. This proximity also creates a thrilling and somewhat unsettling possibility. The 120-year gulf of time and space is a two-way street. Just as we are now receiving light from their world as it was in our past, any intelligent civilization on K2-18b with technology similar to our own could be receiving signals from us right now. Our first tentative radio broadcasts, sent out into the cosmos in the early 20th century, are only just arriving in their star system. As Webb gazes upon their world, they might be detecting the first whispers of our own technological civilization. They might be learning, at this very moment, that they are not alone. We are not just discovering a distant, isolated world. We are potentially making first contact across the void, a silent, delayed conversation between two living planets. But as Webb continued its silent watch, it became clear that K2-18b was not a singular miracle. It was the first clue in a much larger mystery. The telescope began to find other worlds in other systems that showed the same impossible signs of habitability. It was a pattern, a cosmic blueprint for life. The galaxy, it seemed, was not just alive in one place, it was alive everywhere. The distance to K2-18b is both impossibly vast and tantalizingly close. 120 light-years. The number is easy to say, but the reality it represents is a barrier that challenges the limits of human technology and imagination. The light from this living world that now reaches the mirrors of the James Webb Space Telescope began its journey when Theodore Roosevelt was President of the United States, when the first powered flight had barely left the ground. It has been traveling through the silent, frozen void of space for more than a century, carrying its precious message. If we were to embark on a journey to K2-18b today using our fastest spacecraft like the Voyager probes, the trip would take over 2 million years. Human civilization would rise and fall 1,000 times over before our robotic emissary arrived. Yet, in the grand theater of the cosmos, 120 light-years is practically next door, To put this distance in perspective, imagine shrinking the entire Milky Way galaxy with its 400 billion stars down to the size of North America. On this scale, our entire solar system would be smaller than a single grain of sand. K218b would be another grain of sand just a few miles away. In a galaxy that stretches thousands of light years across, this world is a close neighbor, a member of our local cosmic community. And this proximity carries the most staggering implication of all. If a world so perfectly suited for life exists this close to us, then how common must life be throughout the rest of the galaxy?
The discovery of K218b was not an isolated event. It was the first tremor of an earthquake that would shake the foundations of biology and astronomy. As the James Webb Space Telescope continued its silent, patient watch, a breathtaking pattern began to emerge. K218b was not a singular miracle. It was the first page in a vast cosmic encyclopedia of life. The galaxy, it turns out, is not a barren desert with one lonely oasis. It is a thriving, diverse ecosystem, and we are just now opening our eyes to the sheer abundance of life around us. Within a sphere of just 200 light-years from Earth, a tiny, insignificant bubble in the scale of the Milky Way, astronomers have now identified over 50 planets that show signs of habitability. These are not just vague possibilities. These are worlds with atmospheres, with water, with temperatures that fall within the narrow range that life requires. The diversity among these worlds is staggering. They include super-Earths like K218b with their deep hydrogen oceans and stable climates. They include smaller, rocky planets orbiting in the twilight zones of red dwarf stars. They even include potential water worlds completely covered by global oceans and ice planets with warm, liquid seas hidden beneath frozen shells, harboring ecosystems in perpetual darkness. If our immediate cosmic neighborhood is this crowded with life-friendly worlds, the implications for the entire galaxy are almost too vast to comprehend. With its 400 billion stars, the Milky Way could be home to billions of living planets. There could be more inhabited worlds in our galaxy than there are human beings on Earth.
And these worlds are not just ancient relics. Life, it seems, is a constant and ongoing process of creation. In a stellar system just 6.4 million years old, a cosmic nursery where planets are still being born, Webb found another impossible world. Around the young red dwarf star Ce and Lie, the telescope imaged not a planet, but its footprint. The star is surrounded by a vast debris disk, a chaotic ring of dust, ice, and rock left over from its formation. But within this disk, Webb saw a perfect, clean gap. A clear lane swept through the cosmic construction site. This gap could only be carved by the gravity of a hidden world, a young planet acting as a cosmic vacuum cleaner, sweeping up material in its orbit. There, in the faint infrared glow from within the gap, was the planet itself. With a mass similar to Saturn, it is the lightest planet ever to be directly imaged. And its temperature, a perfect 120 degrees Fahrenheit. This discovery is revolutionary. It suggests that life doesn't need billions of years of calm and stability to take hold. It can emerge in the violent, chaotic heart of a planetary system that is still under construction. The planet is growing, still gathering material from the disk, its surface likely battered by constant impacts from asteroids and comets. Yet, it has already developed a stable, warm atmosphere. This tells us that life is not a fragile, delicate phenomenon. It is tenacious, robust, and opportunistic, capable of taking root the moment conditions allow. From the ancient stability of K218b to the chaotic nursery of Ce and Lie, the message is the same. The universe is fundamentally alive. We are not an accident, but an expression of a cosmic imperative. The silence we once perceived in the night sky was not emptiness, but the patient hum of a billion biospheres waiting to be discovered. This realization changes everything. It ends our cosmic loneliness, but it also presents us with a new and profound responsibility. The moment we are no longer alone has arrived. The moment we are no longer alone has arrived. For all of recorded history, humanity has existed in a state of profound cosmic solitude. We have looked up at the silent, star-dusted sky and seen either an empty void or the face of a god made in our own image. Our philosophies, our religions, our deepest fears, and our greatest hopes have all been shaped by the belief that we are a singular, miraculous accident, a brief flicker of consciousness in an otherwise unthinking universe. The discoveries of the James Webb Space Telescope have brought that age to a definitive, spectacular end. We are not an accident. We are a part of a vast, interconnected, and fundamentally living cosmos. Our journey has taken us across 120 light-years of space to the shores of a hydrogen ocean on K2-18b. We have witnessed a world 8.6 times more massive than Earth, warmed to a perfect 120 degrees by a star that will outlive our own sun by trillions of years. We have seen the irrefutable 99.7% certain evidence of life in its atmosphere, a chemical fingerprint that broadcasts its existence across the void. But the story did not end there. From the chaotic, swirling nurseries of young stars to the ancient, stable systems of red dwarfs, a pattern has emerged. The universe is predisposed to life. The conditions for it are not impossibly rare, but common, woven into the very fabric of planetary formation. To be human is now to know that the darkness between the stars is not empty. It is simply the quiet space between neighbors. We are like a child who has spent their entire life believing they live in a silent, empty house, only to one day press their ear to the wall and hear the faint, unmistakable sounds of a bustling, vibrant family in the next room. The knowledge is irreversible. The silence is broken forever. This realization transforms our entire understanding of ourselves. Our struggles, our triumphs, our art and our science are no longer the solitary achievements of a lonely species. They are our unique contribution to a galactic chorus of living worlds. This new reality brings with it a profound and sobering responsibility. We are, by all accounts, a very young intelligence. Life on worlds like K2-18b may have had a head start of billions or even trillions of years. In a galaxy filled with ancient life, we are the newcomers, just now taking our first steps into a much larger and older community. The ethical questions we now face are immense. As we continue to scan the skies, as we catalog more and more living worlds, what is our role? Are we silent observers? Are we explorers? Are we custodians of the precious life on our own world, tasked with preserving it as our unique gift to the cosmos? The James Webb Space Telescope has given us the greatest gift imaginable, the knowledge that we are part of a living universe. The faint light from distant worlds no longer carries just the story of physics and chemistry, but the living breath of other biospheres. The night sky, once a symbol of infinite cold emptiness, has been transformed. It is not a silent void. It is a chorus of a billion living worlds, a cosmic ecosystem humming with the quiet, persistent rhythm of life. And for the first time in the history of our species, we are finally able to hear the music.